Welcome back, everybody. Uh, Hope everybody had a good week. All right, got a number of things we need to go over before we begin. We are approximately, well, not approximately, we are 4 weeks away from, uh, actually 5 from doing our final. So we have 4 weeks left of Zoom lecture time. Okay. We are on chapter 13, which we'll do today, and then I'll jump into 14. And so what I'm going to be doing for the next starting today, chapter 13 through 14, and then next week will be 15, and then the last chapter on the 7th will be chapter 15. That means that we may need a little bit of the following week, which is Friday, but probably not. But that will be considered what I call a study day. And so basically the next few Fridays after I'm done with the lecture and what we're talking about that chapter, whatever time is left over is up for you guys. Yeah, you have any questions concerning whatever the topics are? Remember that the final is scheduled for the 21st. Okay. And I can't, that's 21st. If you need to take it early, some of you already made an asked if you can take it earlier. I don't have a problem with that. We'll fix it up. We'll make that happen, but I cannot take it afterwards because I got to get the grades in the following day. Okay. So think ahead about your schedule, making sure you're going to have plenty of time for the 21st to finish that comprehensive exam. It is comprehensive. It will take over all the chapters that we've been talking about. Probably not chapter 16. More than likely not, given it's the late one in the chapter. So, but it would definitely have chapters 1 through 15. On the course website, there are some old exams. There's some old final exams. Do take a look at those. Those are good resources to give an idea what type of questions were asked in the final. It consists of, I believe, let me double check, about 60 questions. Okay. Maybe 2 or 3 questions per chapter, approximately. And so start organizing your time of what we got left and get ready for that final. I want to make sure that you guys are ready for it. Okay. Now, which brings me to the point. Up to last week's assignments, I have completed everything with respect to grading. Canvas finally started to cooperate, and I was able to get all that completed. So all the assignments, with the exception of the exams. Those exams are one time, one shot only, a certain date. But the homework, the activities, those things, and the labs, those things have been left open after their due date. Okay, and so yes, they all have a due date, and but they're left open. Most instructors cut it off once you're past that due date. You can't go back and do it. Well, I leave it open. However, there is a penalty. Okay, there is a penalty, and at the most, after 5 days, the most points you can get will be 50% of whatever that point is worth. But some points is better than a 0. Okay. Now, what I did earlier last night and today, I went through all the assignments that were due way back when, and I inserted a 0. Now, Canvas, when you don't complete an assignment, it does not put a grade in it. It leaves it blank. And so, in effect, it doesn't really give you a true picture of your current grade, because that grade, or the one you missed, has not been incorporated into the total points. So what I did is I went through all of them, and if they were past due, I put a 0 on them. Now, that doesn't mean you can't do them. It just means that now you have an accurate picture of what your grade is and where you really are. Because what can happen is I've had instances where students have maybe completed a half a dozen assignments, and they did very well on it. And so they were doing like an A. It looked to them, they got an A. But they forgot to do, as the semester progressed, other assignments. And so they went along thinking they're doing good. And then when I put the 0, that A dropped all the way down to a D. And generally, that was a kind of a shock for them. Well, that's your true grade. Okay. So if you didn't complete them, um, it's on you. You go back and complete them. And if you want, if not, keep that 0 there. But like I stated, if you've not done it, and remember the homework's got 2 attempts. Now, one thing about Canvas, not the smartest software in the world. And let's say you have one of the homeworks from way back when, and you only did 1 attempt, and you got an 8, so 10 points. But you decided to go, well, I'm going to go back and see if I can improve that 8. Okay, that's good to go. You can do that. Well, you do it, you improve it, you got a 10. Okay, great. But Canvas thinks that you're submitting a late assignment because it was due way back in, say, February, and so it takes out the penalty, even though you got a 10. Well, if that happens, no problem. Just let me know. If you go back and redo some of the other assignments that to improve your grade, and it is better, but Canvas tells you, no, you got only 5 points. Let me know which one it is, and I would take that penalty off. Okay. Any questions? So right now, everything's graded. We have that homework due today, and the homework that exam, due started. It opened up today, and it will be due tomorrow at, I believe, 10 or 11 p.m. Check the time there. Okay, so don't forget about that. Any questions about that exam number 4? Exam number 5 will be given on schedule for the 14th. And then, like I said, our final is scheduled for the 21st. So it's 1 week before the final. All right. Any questions and comments? No? Now, there are a number of you. I will see what I can dig up as far as a study guide. I believe I've created one. I take that back. On the course website, there should be a document that will give you use as a study guide. Okay. Also, like I said, you look at the old exams. Granted, those old exams were made for in-person coursework, but we took them and we adapted them to work with Canvas. So it'd be a similar type of questions. Okay. Nothing very similar to all the old exams we've done. All right. All right, no problem. There are a number of you that have not completed or not attempted or whatever reason have not done like homeworks and activities and labs. They're still open, and I will give you an early Christmas present if you knock them out before, let's say, I'll send an email. I'll give a due date. If you can knock out those before a certain time, if I look at the calendar, I'll think about it, give you a more accurate picture. But if you knock it out before that date that I select, I will take off that penalty. Okay, so you may want to, if you have a number of them, some of you are missing quite a bit of them, and so you might consider take like whatever number of hours you need to get that knocked out. That nomenclature exam, remember, that is an exam that is 20 questions. You're naming the compound, you're giving the formula. You have an unlimited number of attempts. But as per the departmental policy, a passing grade is in the 80%. So if you do a 75, then I gotta take that off and put a 0. But it's worth 10% of your grade. So it does have a big effect on your overall grade, especially if you're on the border. Okay, you're on the border, it could keep you on the C and prevent you from getting up to the B level. So, you got 4 weeks left here, start going there and start, hopefully you picked up the names. You can do at least 80% of those. If we did it earlier, you won't get the extra credit. The questions you mentioned, if we did it earlier, Oh, yeah. The nomenclature, yes. It's in there. If you did it before the 11th week, let me know, and I get 20% or something like that. Get a couple points extra. If you did do it before that 11-week time period, alert me, and I would give you your extra credit on the nomenclature exam. Okay. Any questions? At the end of the semester, there is a link for evaluation of the course. It takes you to both the lecture and the lab part. And so if you would, when it's not open now, but it will be open here soon. I can't open it until everything's in and so forth. I don't see the results until next semester. I would appreciate any constructive criticism. I get plenty of destructive criticism. So, I need some, what can we make this better? Given that we're doing online, we're kind of limited. I try to turn my kitchen into a lab, but it was a little bit tough to do that and do things. And so it's a little bit different. Okay. So, yeah, challenging with respect to online, but I expect that this type of course, I was skeptical in the beginning a year ago. But having done this now for a year, half of last year's semester, all summer, and all last fall, uh, I compare the scores and how they done with the ones we did in person. It's very comparable as far as doing it online. Obviously, you don't have the touchy of the lab, so that we're considering making that a hybrid and actually have to come in for the lab and then do the lecture on virtual, so we're doing a hybrid kind of deal. So that's things we're looking at. And since some people are doing that right now. So, okay. Any other questions, comments, concerns? All right. Well, feel free. Remember, I also teach the same class Tuesdays and Thursdays. I got a 1 o'clock from 2:15 and then a 4:15 to 5:30. Okay. Same 1:30 class. It just happens to be GCC, but we're using the same textbook. We are approximately in the same chapter. In fact, you guys are just slightly behind them, very little. They're in chapter 14, about halfway done. You're almost done with 13 here. We're going to jump to 14. And so feel free to go in there, same link, and just, sit in and get more information. Okay. Not a problem. Also, FYI, we're doing the study day with GCC, my GCC courses. So every Tuesday, starting this Tuesday, every Tuesday until the end of the semester, that will be a study day. Okay. We meet twice a week, Tuesday and Thursday. So Thursdays will be lectures and Tuesday will be a study day. So again, you have questions. Friday doesn't work for you. Feel free to come Tuesday, 1 o'clock or 4:15. Okay. Same link on Canvas. All right. Any questions? All right. Well, let us continue with where we left off. We were in chapter 13, dealing with stoichiometry. Let me back it up one. But here's the flow chart that I hope you have committed to usage quite a bit with respect to using to calculating going from point A to point B. Okay, because you can go from the top left corner to the bottom right corner. You have grams of a given material. You want to find the volume of a given material at STP, and you follow the flow chart. The key thing to remember is I cannot go directly from grams to grams. I have to go through an intermediate common factor, which is moles. Okay, and we get moles from one or two places. One, the molar mass, which is accumulation of all the atoms in the compound and their atomic weight. Adding those up, that gives us the molar mass for a compound. which has units of grams per mole, which again is a ratio that we can write as moles over gram or grams over moles, okay? And the other aspect that we need is that mole ratio in the center. And that is the stoichiometric relationship between either reactants, be it a one-to-one relationship, saying I need one of A to react with one of B, or I may need two A's to react with three B's, okay? Something to that effect, a one-to-one, one-to-three, any combination there is, that comes from balancing our chemical reactions. So that mole ratio can come refer to the reactants, or they can refer to the products. If we have X amount of reactant, how much of this product we're going to get. Or it could be worded that I need to make an X amount of product. How much reactant do I need to start off with? Okay. So, and we rely on the mole ratio. So it's crucial that you balance your chemical reaction. Otherwise, your mole ratio will be off, which means the moles that you're searching for will be incorrect. Okay. And once you find the moles that you're looking for, now again, if we're in STP, we can get the volume because of the 22.4 liters per mole. Or if we know the molar mass, which we can, we're given the formula, we can calculate it. And if we're not given the formula, we could be given the name of the compound, and from the name, write the formula. That's what we've been doing. Okay, we started with the periodic table. From there, we went to ions. From the ions, we put the ions together in the right ratio to cancel out the amount of cations and anions, right? The specific ratio of each atom, and then put them together. And then these compounds that we created react with each other to make products and so forth. Okay. And now we're doing calculations. All right. So this flow chart is very important with respect to these types of calculations. All right, so the question here says, write and balance the reaction of hydrochloric acid, okay, and solid cobalt. All right, so they're telling you here some additional information. Note that cobalt will be in the +2 as an ion. And that information is important. Why? Because cobalt is not part of the sweet 16. Remember those guys? Remember, those are the 6 metals that you know 100% of the time they have constant oxidation number. Okay, so cobalt's not one of them. That means that we need to know cobalt can have a variable oxidation number. So that bit of information has to be given to us. Okay, and they're telling us that cobalt will be in the +2 state, which helps us out. So let's write down the reaction given what we're given. Okay. So move this out of the way here. All right. So write and balance the reaction of hydrochloric acid, and so we have HCl, aqueous, and so HCl, aqueous. Okay. And which is telling me plus cobalt, solid cobalt. Okay, so it certainly looks like a single replacement reaction, does it not? Yeah, because it looks like we're going to replace cobalt with the hydrogen. The hydrogen, remember the activity series. The activity series that relates the reactivity of metals relative to each other, they are all relative to hydrogen gas. And hydrogen gas, its ionic form is the proton, H+. Okay, and so let's double check that. Okay, we got cobalt, which is more the reactive metal, if you will, relative to the gas. Is it cobalt or hydrogen? So cobalt versus hydrogen gas. Who's more reactive? Well, we go to the periodic table. And in the bottom, you'll see, well, not the bottom, right below the periodic table is the activity series. You look for cobalt, and you'll see, and then you look for hydrogen. Hydrogen will be written with H in parentheses. Okay, that represents either H+ or hydrogen gas. Okay. And so it tells us that cobalt is much more reactive than hydrogen gas. Okay. That's good to know. So the next question is cobalt in an ionic form? Is it in an ion form? No, it's not. It's in elemental form. So that means that we will get a reaction. And obviously, we're replacing cobalt with hydrogen. We're replacing the hydrogen with cobalt, which means that hydrogen gas is going to be created. Okay? Now, with respect to cobalt, they told us up here that cobalt will be in the +2 state. So we need that bit of information. Let me erase some of this stuff here. Okay. And we have chlorides coming from hydrochloric acid. And so that's the anion, counter anion. And we know that the chlorides each have a -1 oxidation number. Chlorine comes from is in group 7. When it becomes the ion, it will be a -1 because it picks up 1 electron, giving us the octet. Okay. If you don't remember that, look at that the compound, hydrochloric acid. This is an acid. We know it's going to create a proton here. That's a +1 proton. Then that implies that chloride has to be a -1. Okay. So here we're going to put cobalt chloride together, cobalt Roman numeral 2 chloride together, to be specific. And that means we're going to need 2 chlorides to counter the +2 charge of the cobalt. And so let me write its formula. And so we have cobalt chloride 2. All right, so we got the formula. Now we got to balance it. Okay. Well, any number of ways you can balance it. You see, you got 2 chlorides here, you got 2 hydrogens here. Just think, I can put a 2 in front of hydrochloric acid, and that balances out everybody, does it not? You got 2 hydrogens in the reactant side, 2 hydrogens in the product side, 2 chlorides, product and reactant, so they're balanced. I got 1 cobalt, and we are balanced. And so that is our chemical reaction that we take in words. We're taking the words and converted them into formulas, and then check to see, well, what type of reaction do we have here? And it looked like, definitely looked like a single replacement reaction. Okay. Couldn't be a double replacement reaction. Why? Because in a double replacement reaction, both reactants are always soluble. They're aqueous form. To create a precipitate is one of the products. Here we got cobalt is solid, right? I mean, we can go through a process of elimination to determine the type of reaction that we have here. Okay, let's do that. Okay, because you might be thinking, well, how do you know for sure that's what it is? Well, remember, there's only 6 types of reactions, correct? And one of those was combination reaction. Right? Combination reaction. That means that 2 elements come together to form a compound. Well, yeah, we got 1 element, but HCl is not an element. Okay, so we can eliminate that. A decomposition reaction. A decomp, again, we start off with 1 reactant, we do some to it, and we break it up into its components. Now here we got 2 reactants, so we can eliminate that factor. A combustion reaction. Okay, well, what do we need when we combust anything? We need oxygen. Well, there's no mention here of oxygen. Plus, we're only combusting for Chem 130 hydrocarbons. Those are compounds that deal with just have carbon and hydrogen. That's not the case here, right? No oxygen, no hydrocarbons. We can eliminate that. Acid-base reaction. Okay. What do we need for an acid-base reaction? Well, we need a proton. Well, possibly we got protons here from hydrochloric acid, but what else do we need? We need the base, the hydroxide. No hydroxide is mentioned here. So guess what? We can eliminate that. And the double replacement reaction, okay? Right, well, we start off with A and B that both are soluble, okay? A and B are both are soluble. Well, here we got one soluble hydrochloric acid, but cobalt's a solid. So that's not the case. It's not a double replacement. Normally, when we have a positive reaction for double replacement, then this could be C, a product which is a solid, and then it could make D, which could be aqueous. Okay, that's the double replacement reaction. That's not the case here. So, what else do we have? That the last thing is a single replacement. It has to be that. And so we look at it and say, well, the single replacement, we got to have a metal in the elemental form, which is what we have, cobalt. And then we have another corresponding. What might throw you off is that we don't have a metal is an ionic form. We have the gas of hydrogen, who all these metals are relative to with respect to reactivity. And so that hydrogen will tell you, okay, we must have hydrogen here. We're going to create hydrogen gas. And that is the case. We just replace the cobalt with the hydrogen. Okay, so that's how I went about to determine what type of reaction do I have. You can keep in mind, there's only 6 types of reactions, and those 6 types are very specific in what's reacting, very specific as far as products that you're making, and so forth, okay? All right, so let me clear my mess. And let's bring on the reaction, and there we go. Here's the reaction to two hydrochloric acid molecules, one cobalt, to give me one cobalt 2 chloride and one hydrogen gas. Okay, now once we have the balanced chemical reaction, we're set to do any type of calculation that is asked of us, okay? Whether they want to talk about reactants or they want to talk about products relative to reactants. Let's see what they're asking. Okay. How many liters of gas at STP will form if you have 5 grams of cobalt? Okay, so liters of gas, obviously the only gas we're talking about is hydrogen here, right? And they want to know how many liters. If we start off with 5 grams of cobalt, okay? So our only concern is the relationship between cobalt and hydrogen that we can see here that is simply is a 1-to-1. We got 1 cobalt reacts with sufficient amount of hydrochloric acid, and in that process we create 1 liter or 1 mole of hydrogen gas. Right. We are at STP, which is another important bit of information, because then keep this in mind, that says that we can use this relationship, 22.4 liters per mole. Okay, so let's work the problem and let's figure out what we got going here. What do we do? As always, we write down what we're given. Okay, 5 grams of cobalt. And I write down what I'm striving to obtain or what the question asks for. And it's asking me to calculate how many liters of hydrogen gas are formed. Okay. All right. Well, the first step, we're in grams. We need the atomic weight of cobalt. Why? Because we want to convert that that grams of cobalt into moles, and I get 58.93 grams of cobalt per 1 mole cobalt. That is from the periodic table. Okay. Notice that when I start in grams, I'm dividing by the molar mass. My units, always keep track of your units there. That shows you that you're going in the right direction. Cancel. Grams of cobalt cancel, leaving me at this point, if I were to stop the mathematical calculation here, I would have units of moles of cobalt. But I'm asked to go to liters. So I need one more bit of information, and that is where we use 22.4 liters per mole because we are at STP. And this is true only, I repeat, only at STP, okay? Moles cancel, leaving me with liters of gas. So with respect to units, the problem is set up properly, okay? Now it's on you to do the mathematics and punch in the numbers and come up with a number. Now, also keep in mind, remember that I stated earlier, if not, I'll repeat it, but this conversion factor, 22.4 liters per mole, is a measurement, okay? It is a measurement, and with any measurement, that last number, there's a degree of uncertainty, okay? So therefore, it's not an exact number. And being not an exact number could play a factor in with respect to significant figures. Yeah, those sig figs never go away, do they? No. Remember I said way back when sig figs play a role in science from all the way from the beginning of the semester to the end. So no, they don't go away. And so the 22.4 liters with 3 sig figs could be a factor with respect to the answer, or it could not. Obviously, the atomic weights are not. Atomic weights are not used to determine the sig figs because those are averages of whole numbers, and those have an infinite number of decimal places when you average out a whole number. Think of it for yourself. You know, average out 4 and 5. What do you get? 4.5. It's a decimal number. And so I could theoretically just write 4.50000000 to whatever numbers I need. So that's why we don't use the atomic weights, but do use the atomic weights given in the periodic table that we supply. Okay. Because those atomic weights are geared for the answers in Canvas. If they're off a little bit, Canvas may not understand the answer, even though you may be off at hundreds, even, you know. If your answer is that off and you know it's right, as always, send me an email. I'd be glad to check it and make sure everything's up to par. The number's correct, and I'll give you credit for it. All right, so we set that up. We set the problem up. Let's clear my mess and let's bring in the good letters. Okay, so we got 5.0. Write down what we have: 5.00 grams of cobalt. All right. Our first step is to convert the grams into moles of cobalt, which require us to take the atomic weight. I say, okay, when I say atomic weight, molar mass, the only difference between the two is this: atomic weight, we're dealing with one element, okay? So atomic weight of what's on the periodic table, those are atomic weights. Molar mass is the sum of all the atoms in the compound. So H2O has a molar mass of 18.02 grams per mole. That's because there's an oxygen and 2 hydrogens, okay? That's the molar mass. Okay, so that converts us to moles of cobalt, right? Now, we then, I missed a step, okay? Because I need to convert the moles of cobalt to moles of hydrogen. So I use a stoichiometric relationship. I can't believe I missed that. I went directly to the answer. Okay, because unit-wise, let me make sure we understand this correctly. Okay, my bad here. This is a very important relationship that we obtained from the balanced chemical equation. Okay, now we took the grams of cobalt, we divided by the atomic weight to give us moles of cobalt. Now we want to get to moles of hydrogen. Well, obviously we need the relationship from the balanced chemical equation. You can see that moles of cobalt cancel. So at this point, now we are in moles of hydrogen. Okay. That's the common factor between the hydrogen and the cobalt. I can't go directly from grams to liters without having to go through moles. And of course, being an STP, then I can introduce the final unit to get me into liters of hydrogen gas. Okay, and so my moles cancel here. And now I'm in liters of hydrogen gas. 3 sig figs. Let me clear up my mess a little bit here. 3 sig figs here. I got 3 here, and I got 3 here. Okay. We don't use these for sig figs as the atomic weights or molar mass, and we don't use the stoichiometric relationship because those are whole numbers. They're exact numbers. Okay. All right. So if we start off with 5 grams of cobalt, we will obtain 1.90 liters of hydrogen gas. All right, one more question. If we have 2.374 liters of hydrogen gases formed, how many grams of hydrochloric acid reacted at STP? So what are we looking at? 2.374 liters of hydrogen gas. So 2.374 liters of hydrogen gas, okay, were formed. How many grams of hydrochloric acid reacted? How many grams? Is the question. So our relationship is between here and here. Okay. Bear with me 1 second, please. I need 2 minutes. Okay, sorry about that. All right, so here we're asked 2.37. One more question. Somebody has a question. Oh, Kathleen, you got it calculated. Very good. Let's double check you. All right, let's find out. All right, let's go through it. And let's first write down what we're given, obviously. Okay, and so we are given 2 point. In fact, I'm going to go ahead and do Write down what we're given. Okay, we're given 2.374 liters of a hydrogen gas. That is how much was formed. So we need to calculate how many liters, how many grams of hydrochloric acid. So we need to convert the liters of hydrogen gas into moles. And thankfully, we're at STP and we can do that. If there's no mention of STP, then you cannot go any further because you don't have enough information. We're learning in chapter 16 that there's another equation you can utilize, but at this point in time, this is only true. STP is only the 22.4 liters per mole is only true at STP. All right, so this gets us into moles of hydrogen gas. The next factor comes from the balanced chemical equation. And that stoichiometric relationship is a 2-to-1 ratio, 2 HCl's for every hydrogen. Okay. And so notice the units here as we're progressing. We are canceling the units. So you can see here, cancel as you go along. Our liters of hydrogen gas are canceled here. Moles of hydrogen gas are canceled here. So at this point, we are now in moles of hydrochloric acid, which is what we needed to get to, okay? But we need to be in grams. And so we need one more conversion factor, and that is the molar mass of hydrochloric acid. That's 1 chlorine, 35.45, 1 hydrogen, 1.01. Its molar mass is 36.46 grams of HCl per mole of HCl, and I get 7.72. Okay. So, Kathleen, do you see the difference in our number there? Let's double check my units, make sure. Yeah, double check my math. You know, I could have been out in left field here when I typed in the numbers. But let's check the units, make sure that moles of HCl cancel, leaving me with grams of hydrochloric acid, which is what we're looking for. And I just double checked the number, and sure enough, I have 7.72. Notice the sig figs here, folks. 3 sig figs here, right? Now, we don't use these, the atomic weights, and we don't use the mole ratio, right? They're whole numbers, but the 22.4 is a measurement. It has 3 sig figs. Our beginning problem has 4 sig figs. So our answer should be in 3 sig figs. Okay. All right. Okay. You got the incorrect mass. I see it. All right. Well, which brings me to a point. Okay. Like Kathleen just stated in her chat that she put in the incorrect mass. And that happens all the time. But like I said, this is what when we say show your work, this is what we're talking about. Okay. This answer could be, you know, this whole thing could be worth, let's say, 5 points. And I use this as an example. All right, so the answer itself is maybe worth 1 point, and then the rest of the other 4 points are spread out amongst how you set that up. And so, for example, if Kathleen, you would have put in your answer of 6.246 and shown nothing else, obviously I can't give you any credit, right? But if you show your work and you wrote in 6.246, which obviously is incorrect, I would I still give you a point for showing the work, but I couldn't give you the points for the answer. The point being is showing your work is, to me, is what's more important than you getting the right answer at this time. The fact that you set it up properly and you show how you set it up, that's more important at this point in time than the answer. Yes, you want to be accurate with your numbers. You know, in your professional life, you got to show accuracy with numbers, and you don't want to mess that up, but mess it up here in class and not out there in the quote real world. Okay. All right. So let me clear my mess here. Here's a problem, another word problem. First thing we got to do is convert it to an equation. So we have hydrochloric acid, gas, HCl gas. Something interesting. Normally we think of hydrochloric acid, okay? And it's interesting that when it's a gas, HCl, we call it hydrogen chloride, okay? When it is a acid, being an AQ, we call that hydrochloric acid, okay? Notice the difference. So be careful when you do the nomenclature. If they say HCl gas, then they're talking about hydrogen chloride or hydrogen bromide or hydrogen iodide. If they got the AQ in there, then they're talking about hydrochloric acid with respect to name. So we got HCl, hydrogen chloride gas, plus oxygen gas, produces chlorine gas and water vapor. So let's write that equation down. All right. So we got HCl gas plus oxygen. Now, this is the mistake that people make sometimes. They forget they're talking about gas here. They didn't say the oxygen atom, they said oxygen gas, and it's diatomic. Okay, we have 7 diatomic elements. Oxygen is one of them. Okay, produces, which is the arrow, chlorine gas. Okay, another diatomic. Gas plus water vapor. So again, we're in the gas phase. So they must be doing this reaction in the very warm conditions. Okay. So what's going on with my mouse here? My pen. Okay, that's not any better. All right, so we have the reactant. Now, next thing we do is we got to balance it, right? Okay, but we got the reaction there. So we can do multiple things here. What if we start off with, okay, we got 2 chlorines here, but I got 2 oxygens here. So what if I do 2 here in water? That's one way to go. And then what that does is gives me 2 oxygens to balance my oxygens, but it kicks up my hydrogen to 4. And so what if I put a 4 in front of HCl? That kicks up my hydrogens, they're balanced, but it kicks up my Cls. All right, so my Cls now are up, so I got to put a 2 in front of chlorine. Let's see my balance. I got 4 hydrogens here, 4 hydrogens here, 4 chlorides, 4 Cls, 4 Cls, 2 oxygens, 2 oxygens. Looks like it's balanced. All right, let me clear my mess and bring in the actual equation here. There we go. Yeah, it's balanced. So our ratio is 4 HCls to 1 oxygen to give us 2 chlorine gas and 2 waters in the vapor phase. Okay, that is our chemical reaction. So now let's mark who are the parties of interest. How many liters of chlorine? So we're talking about the chlorine can be formed if we have 3 liters of oxygen. So if we got 3 liters of oxygen, how many liters of chlorine? So that's who we are concerned about. Okay. So write down what we're given, 3 liters of oxygen, right? We are at STP, so we can convert those liters to moles. Then, of course, the central mole ratio combination, stoichiometry relationship, I should say, which is a 2 to 1, goes here because now we're that puts us into moles of chlorine, okay? And being still at STP, okay, then I add the 22.4 liters per mole, and that being the case, that should be 6 liters of chlorine. Now, can you see something here in our calculation that we can do to, I don't know, streamline the calculation setup? Is there anything here you can see here that you can do? Take a look at our reaction here, I mean, our calculation. Do not the 22.4 liters cancel out automatically, okay? And so basically, we are needing only, yeah. Well, the mass, I'm not sure about the mass of what you're saying. We're talking about the volume here, but the mole ratio is what we only have to utilize. Now, you can do that only when everybody, all the ones you're calculating are in the gas phase. Meaning that I can eliminate the 22.4 liter per mole relationship if I want to go from HCl to water vapor. They're both in the gas vapor, so I don't have to worry about the 22.4 liters. I can go directly with the stoichiometric relationship. So if I had 1 liter of HCl, okay, who can tell me this? If I have 1 liter of HCl, how many liters of water will I make at STP? Let me clear this up. Maybe I might. I got too much junk going on here. Let's do it this way. If I have 1 liter of HCl, how many liters of water vapor would I make? Who can tell me that? One liter of HCl, how many liters of water would I make in the gas phase? How about 2? Yeah, exactly. 2. Ezra, because, you know, given that we're going from gas to gas, we are at STP. We can eliminate the 22.4 liters and we can just simply go with the mole ratio. In the balanced chemical equation. Okay. Oh. Okay, you want to rethink the answer now? I got 1 liter of HCl. How many liters of water would I make? 1.5, exactly. Okay. And I can eliminate these again only when we are at STP and we're going from gas to gas. Okay, if one of these would have been a liquid or something else, then no, we can't do that. Only from going from gas to gas. All right, good. You might want to try these at home, okay? This is a good example of something. Try this at home, and maybe next week you can bring it in, or maybe later on after class or after we finish with. We might finish with 14. I'm not 100% sure. It depends on the questions and so forth. Anyway, if carbon reacts with oxygen gas to form carbon monoxide, okay? Now, how many liters of carbon monoxide at STP can be made from 15 grams of carbon? If you got 15 grams of carbon, how many liters of carbon monoxide can you make at STP? That's the first question. Then the second question will be if you have 20 liters of oxygen, okay, how many liters of carbon monoxide at STP can be made from 20 liters of oxygen or 15 grams of carbon? And you should come up with 28 liters of carbon monoxide for the first one and 40 liters of carbon monoxide for the second. Okay, so I won't show how the setup, but work it through, see if you can work that problem through. All right, got a quick overview on these calculations. Okay, we started with the elements as I talked about, and from these elements we created compounds, either ionic or covalent compounds. Now, once we did that, we took the compounds and we started to react them with each other, and we started to learn how to balance chemical reactions. Okay. Then from the balanced chemical reactions, once they're balanced, we have coefficients that gives us the stoichiometric ratios of the reactants and the products and their relationship with each other. And bear in mind that balanced chemical reaction, that those stoichiometric relationships are true whether we make half a gram of material or we make 10,000 kilograms of that material. The same ratio applies, okay? And so we can do calculations on reactants and products based on the ratios, and we can do them in terms of moles, do it in terms of grams or liters if we are at STP, okay? And that, again, I can't overemphasize this flow chart to help you go through these calculations. And as you go through these calculations, follow the flow chart. Use it as a guideline to help you to get from point A to point B. The key thing, as I stated before, is moles. We cannot go from apples to oranges, so to speak, unless we go through moles. And moles is what relates an apple and an orange, if, for example, okay? All right. That, ladies and gentlemen, brings you to the end of chapter 13. Congratulations. 2 more to go. 3 more to go. What am I saying? And they're fairly short. All right. Does anyone have any questions? Okay, I tell you what, it's almost 2 o'clock. Why don't we take like a 10-minute break? Okay. Come back at 2:10, and then we'll continue with chapter 14. This takes a little bit longer. Chapter 14 deals with what is called intermolecular forces, and it's all related to those crazy electrons. All right. So let's take a 10-minute break. We'll come back 2:10. All right. Let me pause. Okay, welcome back. All right. So, any questions before we continue with 14? All right. Well, let's continue. Chapter 14. This deals with forces, specifically what are called intermolecular forces. These are forces that occur between molecules, I-N-T-E-R. these forces have a big factor on the properties of compounds, why certain things boil at a certain temperature, why some of them are very volatile and evaporate very readily, why some of them are very thick, flow slower than, say, other liquids at, say, room temperature. We're always talking about room temperature, 25 degrees, okay? So these forces are all related to electrons, these electrons around these molecules and how they interact with each other. And we're going to start learning about these forces. But before, and there's only 4 forces to deal with. Okay, 4 types of forces. We'll get into that. But before we deal with this, I'm gonna refresh our memory with respect to the 2 types of compounds, because we need to learn how to determine one is, okay, it's a covalent compound. Refresh our memory how to determine whether this covalent compound is polar overall or non-polar, okay? And we're just gonna very quickly go over that. Let me call up my whiteboard here for a second. Now, if we're all familiar with ionic compounds, right? One of the requirements of ionic compounds, and ionic compounds, the requirements, C shorthand, CPTS compounds, was a metal combined with a non-metal combination. So, for example, sodium chloride, we're all familiar with that. Also, remember that these ionic compounds have a full-fledged charge on them. The sodium has a full-fledged positive charge on it, okay? And the chloride has a full-fledged negative charge on it. And they come together and they attract to each other simply because of the charge. And it's like an electrostatic charge, like two magnets coming together, attracting. They never really make a bond. Okay, there's no bond. It's an electrostatic attraction between the two. All ionic compounds exhibit solubility to an extent in water. Okay. Yes, by the solubility rules, some ionic compounds are 100% soluble, making them strong electrolytes. But the ones that are insoluble, even though they're classified as insoluble, they do have a few ions in solution, and the bulk of it is together as a solid. Okay. Now, with respect to covalent compounds, I know this might be redundant and rehashed, but we need to make sure we're all on the same boat. We have nonpolar, I call that NP, and polar, P, covalent compounds. The difference being is nonpolar is 2 nonmetals, because we have nonmetals combined with nonmetals. Nonmetals hooked up with nonmetals, NM, NM, nonmetals. So carbon dioxide, for example. Okay. Now, let me clean up make a little more room here. Oh. All right. Now, this is a challenge I found over the semesters, and distinguishing between the two when you got a polar nonpolar. And it's very straightforward. I want you to just think of it in generic terms, okay? For a nonpolar species, I'm just using the letters A to represent some element bonded, guess what? To the same element, A bonded to A. That's it, okay? Don't care what A is. All I know is they're the same thing, okay? Now, way back when we talked about electronegativity, okay, with respect to covalent compounds. And electronegativity was the affinity for atoms to want to pull electrons onto itself in a bonded pair. So when an atom is bonded to something else, another atom, depending on its electronegativity, it's going to want to draw those electrons in that bond toward itself if, in fact, it has a higher electronegativity. When you have A and A together, they are both the same element. Therefore, there's equal sharing of those electrons right in there, okay? Equal sharing. Those electrons are distributed equally. There's 2 electrons in that bond. Or it could have been 3 electrons, or, 4 electrons, or 6 electrons, single, double, triple bond. But those, if AA are the same, then there's equal sharing, and we have a nonpolar bond, okay? Nonpolar bond. Once we identify that, we're good to go. There's only one force that deals with nonpolar bonds. Now, the other exception to this was, remember, the carbon-hydrogen bond. We consider that a nonpolar bond, simply because the electronegativity between carbon and hydrogen, for all intents and purposes, is the same. So they act electronegativity-wise as the same element. Therefore, they have a nonpolar bond. Now, as a guideline, when a compound has all nonpolar bonds, all nonpolar bonds, okay, we have a nonpolar molecule. Straightforward. So all the hydrocarbons out there, nothing but carbon, hydrogen, nonpolar bond. Okay, all the diatomic elements that we have no fear of ice cold beverage, nonpolar bond. Okay. Now, let me clear up a little bit here. With respect to polar bonds, again, very straightforward. When I have A, again, whatever A is, and I have a different element, doesn't make a difference what it is, with the exception of the carbon hydrogen, okay? That's, like we said, nonpolar. But if B is whatever else up there, non-metal, then we have a polar bond, plain and simple. Nothing more complicated than that. Why? Because A and B exhibit different electronegativity values. They're not the same element like AA, okay? And so the fact that there's 2 different elements, I have a polar bond. That's a given, polar bond. Where you got to analyze it a little bit more is what happens to these polar bonds. As a general guideline, if a molecule has all polar bonds, or any polar bond, okay, and they do not cancel out, then you have a polar molecule, okay? If the polar bonds don't cancel out, and you got at least one polar bond, but if you got more than one and they don't cancel out, you got a polar molecule. If they cancel out with respect to how they are in space, relatively speaking, then you have a nonpolar molecule. How's that? Let me go and go through some examples to refresh your memory. Way back when we were doing Lewis dot structures, we did carbon dioxide, okay? And we did the Lewis dot structures. Now, you may still need to do the Lewis dot structures, because from the Lewis dot structures, you're going to be able to determine, if you don't know for sure, whether you have those polar species or not, okay? Now, the carbon oxygen, that's an example of an AB bond, okay? In both directions. Totally different elements. Guess what? Polar bond, okay? I got a polar bond on the right side. Now, the electronegativity of oxygen is much greater than carbon. Why do I know? How do I know that? Well, I use the periodic table. Fluorine, oh, refresh your memory again. Fluorine is the most electronegative element on the periodic table. And when I want to compare two other elements with respect, when I compare their electronegativity, I look at their position of where they're at relative to fluorine. And whoever is closer to the fluorine, guess what? That is the most electronegative. And so oxygen is about right here. We got nitrogen and we got carbon right there. Okay. Oxygen is a lot more electronegative. I don't have to memorize its value. It does have a value for electronegativity, but I don't have to memorize it. I just find it on the periodic table, compare it to where carbon is. Oxygen is greater in electronegativity because it's closer to the fluorine. So I can write that arrow, that dipole arrow, going from carbon to oxygen. Remember that arrow? Okay. What that means is that oxygen now has a partial negative character because having a higher electronegativity, it tends to pull those electrons in that double bond toward itself much greater than carbon can. So in the result is carbon has less electron character, negative character, and becomes more positive character. Okay. The same is true for going in the other direction. The arrows is written from right to left because again, we have a partial negative. That symbol partial is a lowercase delta, the Greek symbol, and a partial positive on carbon. That's why carbon dioxide is very reactive. We can react it because there's two partial positives. We can react it with, well, that's another story. Anyway, now these arrows are, if you recall, are what we call vectors. Vectors are mathematical entities that have magnitude and direction. Okay, direction meaning positive direction or negative direction. We have a scale going to a positive way or negative way. And that length of the arrow represents the magnitude. Since carbon and oxygen have the same elements, the magnitude of the arrow, I try to draw it similar, is the same. The length of the arrow is the same. However, the direction is different. The one on the left is going in the negative direction. Remember your scale, here's 0. Going in this direction is in the negative direction. This is negative down here, and that's positive, and that's positive. Okay, going up and going to the right is positive. Going down is negative, and going to the left is negative. And so what happens is if we were to add up the polarity or the dipole arrow of left and right, guess what? They cancel each other out. And by canceling each other out, though they have polar bonds, overall the molecule is nonpolar. Okay. Once we know that, now I can select what type of force, intermolecular force, carbon dioxide will have. Okay. Now, the other place example where polar bonds will cancel out is the tetrahedral position. And so if we get, for example, a tetrafluoride compound, that's carbon with 4 fluorides bonded to it, I can draw this three-dimensionally, kind of three-dimensionally like as follows. Got the 2 fluorides here on the plane of the whiteboard. The wedge here represents a bond coming out of the screen. And that hatch mark represents a fluoride going to the back of the screen. So it gives you the tetrahedral 3-dimensional space. Now, carbon tetrafluoride has 4 polar bonds. Okay. Here's another example of A-B bonding. A-B, different, carbon fluoride. And that being the case, I have 4 dipoles. And obviously it's going to the fluoride because fluoride is the most electronegative element there is. And so the fluorides are all going to away from the center carbon to toward the fluorides because the fluorides are really yanking on those electrons and pulling on them. Okay. Not pulling on them so great they become ions, but they have a very high partial negative area on each fluoride. But because of the geometry of a tetrahedral position, all these 4 bonds cancel out. And so the result is we have a non-polar compound, though we have 4 polar bonds. The fact the geometry is such in the tetrahedral position that they all cancel out. Now, let's see what happens. If I were to change one of these fluorides to, God, make it anything, anything other than a fluoride, I could make it into, let me see, let's make it into a chloride. If I make that into a chloride, yes, it's a polar bond. But you know what? The magnitude is a little bit different. And so that arrow is a little bit smaller than the yellow ones, okay? Because the chloride has a different electronegative value than the carbon and then the fluoride. And so the result is, even though it's tetrahedral, the magnitude of this, I'm going to have some leftover polarity because all 4 do not cancel out, okay? The fact that I got one bond is a little bit different. I'm going to end up with a polar compound once I change one of those 4 fluorides to something else. And I put chloride, but it could be hydrogen, it could be anything else. So now it becomes polar. And if I continue to go around the horn and I change that fluoride with chloride, I still same thing, polar. And I keep going around the horn. I got 3 chlorides, 1 fluoride. There is a difference in the polarity of each bond, then I still have a polar bond. Is when I go and I change the last one to a chloride, guess what? I'm back to a polar bond, non-polar bond, excuse me. Okay. So even though you have a polar bond, if they don't cancel each other out due to the geometry or the geometry of the molecule, you end up with a polar molecule. Otherwise, it is non-polar. For example, hydrochloric acid, HCl. We got a polar bond. Well, you say, well, how do I know that? Isn't that an AB situation? It's not an AA situation, right? Because I got a hydrogen and a chloride, so I got a polar bond. Okay. All right. So let's go back to this. Why do I want to refresh my memory on that? That's because of these forces. Okay. What we look at, we're going to be looking at both. We already did the intra, but we'll bring them back. The intra forces, intramolecular forces, are forces within the molecule. There's basically the bond. And so this is intra. That's what type of bond you're dealing with. Okay. But the inter is this interaction between molecules. And this dotted line that it's written here represents that type of interaction. Sometimes that interaction could be very strong, and sometimes it could be very not so strong. Okay. I'll give you an example. You get water, for example, boils at 100 degrees Celsius or 212 Fahrenheit, about 100 degrees Celsius. It's pretty high temperature. But you have alcohol, ethanol, which boils around 78 degrees Celsius. Now, in both cases, they're polar, okay? And you will find later on that they both had the same type of polar character. But there is a big difference because of the structure of ethanol and water, such that it makes the interaction between molecules of ethanol much less. And that's this area here. The intermolecular forces, there's much less. Hence, when I boil it, it requires lower temperature, 78 degrees, to break up this interaction. Okay, compared to water, where the interaction is much greater. Another example would be a cup of honey and a cup of water. We all know that if I empty both cups at the same time, the race, and we had a race, who's going to empty the cup first? Obviously, the water will, compared to the honey, because the honey is very thick. It's very viscous. While the molecules of the honey have a lot of intermolecular forces that interact with each other much greater than the water. Hence, they flow much slower. Okay. All right. So these are the type of forces that we're going to be talking about. Now, these forces are not bonds, they're interacting. Okay. And so they're much weaker than bonds. Bonds, to break a bond here, like this here written here, take a lot more energy than to break the interaction between them. Okay. So it's just the interaction. All right. So let me clear my table here. Now, bonds versus IMF. Okay. We know that one hydrochloric acid molecule and that holds a hydrogen atom in the chloride atom, that is a polar valent bond. Okay. And you might say, well, wait a minute. How do we know that? Well, we know it's covalent, right? Because it's hydrogen and chloride, both of them non-metal, so they're covalent. So now the subcategory is, are they polar or non-polar? Well, again, using the AA and the AB analogy here, this is an AB analogy automatically. It's a polar bond. There's a big difference in the electronegativity between the hydrogen and the chloride. Big difference. Chloride's a lot more electronegative than the hydrogen. So we have a dipole. Remember the dipole? Two poles, di meaning two. So we draw this arrow going from the hydrogen to the chloride with the plus on hydrogen. So we have a partial negative and a partial positive on the hydrogen. Now, this interaction, the chloride is the difference in electronegativity between the two is pretty great. If it was any greater, it would be more like the two ions where you have a ionic compounds, you have a metal and a non-metal. But with acids, that difference in electronegativity is high, and that is why HCl, when we dissolve it in water, dissociates into the proton and the chloride, because the chloride is really pulling on those electrons pretty hard, because the electronegativity of hydrogen is way over in the left field of the periodic table. And the chloride's right next to fluoride, okay, right below fluorine. And so it's very high in electronegativity. So that bond is pretty easily broken up just by simply dissolving in water. Okay. But that's only true for covalent acids. And covalent acids. Okay. And having the fact there is a partial positive and a partial negative, well, think about this. The fact that there's a dipole in both of these going in that direction, at the right, creates a partial positive side on the hydrogen in one molecule, and we got a partial negative on the other side. And so you can see here that this interaction can continue as another molecule of hydrochloric acid. Okay. And here we drew it in, that's a negative. We drew it in a linear sense, but think of it three-dimensionally, okay? Above and below and all the axes, X, Y, and Z axis. So these interactions are pretty three-dimensional. It is three-dimensional. And and they can be very strong. And it kind of gives it somewhat of an ordered state in solution because the interactions are interacting with each other loosely, but still kind of ordered state. Right. So the four types of forces, okay? There's only four types. And these are interactions between the partial positive and the partial negative charges within the molecules, or between the molecules, I should say. The very first type, that is called the London dispersion forces. That is there's four types. Only three of these deal with covalent compounds. The fourth one deals more with ionic compounds. But of the three covalent forces, London forces is the weakest force. Okay. Then we have what we call dipole-dipole forces. Well, it's if you think about it, just like the HCl, we have a dipole here. This is a dipole, right? Two poles. And this is a dipole. Hence, we got dipole-dipole interaction. That is the action between molecules that each have a dipole. Okay? Remember, two poles, north and south, plus and negative. All right. Okay. Then we have a third one. This is a special. It's a special type of force. Yes, it is a dipole-dipole interaction, but because it only occurs with hydrogen and only three specific types of atoms. Specifically, when there is a hydrogen bonded to a nitrogen, or a hydrogen bonded to an oxygen, or a hydrogen bonded to fluoride. Okay, these three here, we call that NOF, not on file. When those hydrogens are bonded to those, yes, there is a dipole, but there's an additional factor, force, that is stronger than just a simple dipole-dipole force. And that is called a hydrogen bridging force. It's a very strong force. Okay. That's what makes hydrogen boil at 100 degrees. Excuse me. Okay, very specific force. All right, now, and finally, the fourth one is called the ion dipole force. Now, if you think about this, the term ion tells you we are dealing with some type of ionic compound. Okay, so some metal, non-metal species. And dipole forces, we are dealing with a solvent, a solution that these ionic compounds are in. Most of the time, we are dealing with an aqueous solution. Water is the one with the dipole. The majority, 99% of the time, it's an aqueous. So if you look at questions and they specifically talk about a ion, then you're going to number 4 automatically, because the first three only refer to covalent compounds. Okay, be it polar or non-polar, they're covalent compounds. Oh, by the way, somebody asked about the PDF files for these PowerPoints. I just in the break. Oh, there's a question here. Okay, Christine, you found it. Good. I went ahead and I went to each module during the break, and I put them in the module for the chapter, so you don't have to search for them. Okay, so they're there. They're all there. And all it is all these, and some of these slides I don't use anymore. You'll see them, and you'll see that I didn't use them, but slides about the same. There's some changes here and there over time, but they're basically the same. And I can't give you the the PowerPoint slides, but I can make them into PDF files, and you can have those. I put them as one up. Okay, so the first three deal with covalent compounds, be it polar, nonpolar, and the fourth one deals with ionic compounds and most of the time in aqueous system. And that's how you can distinguish very quickly. Of the first three, 1, 2, and 3, number 1 is the weakest. The strongest is number 3. And then number 2 is in the center. Okay. Now, with that being said, here's strength would be strongest, weakest, and then somewhere in the middle. Medium, I guess. Okay. As far as strength of interaction, that's trying to break up that interaction between the molecules. And this is why it's important that we first figure out whether the molecule is polar or nonpolar. Because once we figure that out, then we can assign either 1, 2, or 3. And then we add some additions. Here's number 1. All nonpolar compounds, the only force they deal with is number 1, plain and simple, nonpolar. Okay. That means all the other polar compounds deal with 2 and 3 with respect to covalent compounds. Now, number 3 is very specific. Number 3 is only when you have hydrogen to nitrogen, oxygen, or fluoride. That's it. Those 3 elements, nitrogen, oxygen, and fluoride, only with hydrogen on them. Okay. Then they have hydrogen bridging. What does that tell you? That everything else that's polar is dipole-dipole forces. Okay. Dipole-dipole forces. So, I mean, very quickly, you can see that when you're dealing with ammonia, remember that formula for ammonia, NH3, H2O, and hydrofluoric acid, we dealt with those, okay? There's three examples of compounds that, yes, they have a dipole-dipole force, but because they have a hydrogen bonded to nitrogen, oxygen, or fluoride, their stronger force is hydrogen bridging. All right. There used to be a name for this. They used to call it hydrogen bonding, and you may see it occasionally someplace, the term hydrogen bonding. We're trying to stay away from that term because it's not a true bond, okay? It's not a true bond. It is an electrostatic attraction between the two. There's no sharing of electrons. So we're trying to stay away from the term bonding, hydrogen bonding, and use hydrogen bridging force. Okay. All right, so here, let's clear this up a little bit. All right, dispersion forces, the very first one. They're temporary. Actually, they're not very strong, and they're only between nonpolar molecules. So all the diatomic compounds, okay? All the diatomic compounds, there's only 7 of them. Anything with carbon, hydrogen, all carbon, hydrogen bonds, those are nonpolar. And any compound that has polar bonds that cancel out, like carbon dioxide, and let's say the carbon tetrafluoride, the example we did, all nonpolar. And so their only force is London dispersion force. Okay. And what happens is these guys are, like I said, temporary. And the result is the reason how they form is as follows. The best analogy I have for you is the balloon and rubbing the balloon on your head. I use this quite a bit, but this explains these London forces here. Okay, because I think we may have talked about this way back when. I said, well, why is it when you get a balloon, you rub it on your head and it sticks to your chest? And I went through the explanation. As you rub the balloon on your head, it transfers those electrons on your hair. We are loaded with electrons all around us. You know, they're in our body, but there's a lot of them on the surface. We call it static charge. walk on a carpet, drag your feet on a carpet, then touch something, see what happens. You build it, you're getting charged up, and then you release it when you ground yourself. So these electrons are all around us. So we're rubbing that balloon on your head. You transfer some of those electrons from your hair onto the surface of the balloon. Then you take that balloon and you move it toward your chest. Now, as I stated, there's electrons all around us, and even on your chest, there are electrons on the surface. They are negative charge. The balloon has negative charge, right? And so as I bring it to the surface of my chest, those electrons repel the electrons on my chest, causing the electrons on my chest to kind of move into my body, resulting in a partial positive area on my chest. Okay. The balloon has a partial negative area. And guess what? They attract each other because of difference in the charge. Okay. And the balloon hangs on to my chest for a short period of time. Eventually the balloon will fall off, right? Okay. Well, the similar thing happens with nonpolar compounds. These electrons are around the molecule, and as they come close to each other, obviously they're going to push those electrons from the adjacent molecule in a different direction away. The result is you form a temporary partial positive and a partial negative area, and therefore you attract a temporary attraction between the two nonpolar molecules. Now, the last point there says bigger molecules have more electrons. This stands to reason. If we were to compare, say, fluorine gas with iodine, okay, iodine is much bigger. So both of them are nonpolar. F2 and I2 are nonpolar, but because iodine is much bigger, there's more electrons around it, more areas for attraction to occur, and therefore its London dispersion force will be greater for I2 iodine than for fluorine, okay? Just simply because of the size. And that's what they're telling you there with the last entry. And so this diagram kind of shows you what's going on. The two diatomic nonpolar species, and I'm just saying diatomic, but it could be any diatomic compound coming together. The electrons kind of shift for a temporary. We got a partial negative area here created and a partial positive, much like the balloon scenario I explained to you. Okay, well, the result is that we create a interaction here between two molecules, okay? And these are London dispersion forces, and they're very weak. They really are. It doesn't take much energy to break those up, okay? But again, the interaction occurs because of this induced dipole, okay? Here's a term, induced, I-N-D-U-C-E, induced dipole. We have induced a dipole here, okay? It's temporary. Unlike hydrochloric acid, okay, where we have a dipole permanent, but because of the nature of the beast, chloride being much more electronegative bonded to hydrogen, you have a permanent dipole. It's there, it's not induced, it's not created, it's there permanently because of the difference of electronegativity, okay? So we've induced a dipole, a temporary dipole for nonpolar species. All right. Now, with respect to dipole-dipole forces, I explained this one earlier, but here's, again, hydrochloric acid. The chloride has the partial negative side. Hydrogen has the partial positive side. And the effect is, again, this is a permanent dipole, as I explained. And it's the nature of the beast for this polar molecule. And we create this, it has naturally this interaction between the partial negative and the partial positive, okay? And it's a little bit stronger than the dipole, the London dispersion forces, because those are temporary, these are not. Okay. Now, moving on, we well, let me stop here. Obviously, as I stated, this is stronger. The dipole-dipole force is stronger than London forces, and of course, it must be a polar species, okay, a polar molecule. Without that, then you don't have your permanent dipole. Now, with respect to hydrogen bridging, this only occurs for those species, those hydrogens bonded to fluoride, oxygen, or nitrogen, NOF. And very strong interaction, very strong. You can see in this particular picture, you have a partial negative side of the water, partial positive on the hydrogen, okay? Because there's a very strong dipole going in to the oxygens in both directions. That's why water is so polar. Okay. Now, we only show a one-dimensional picture here, but again, think of three-dimensional. You can see how these forces interact all around. Okay, all around the water molecules, and so very, very strong. And so we heat something. What we're doing, and we're trying to break up these interactions. And that's why it takes so much energy to boil water. Okay, it takes 100 degrees of energy to break up those interactions so we can get water out of the liquid phase and move on up through the vapor phase. Okay. Hydrogen bridging, stronger than dipole-dipole interactions and much, much stronger than London dispersion forces. But nevertheless, they are weaker energy-wise than the actual ionic and covalent bonds, okay? Much weaker. Finally, the last force you can see here, this is called the ion dipole force for aqueous systems, okay? The sodium ion given here is, as you know, has a full-fledged positive charge. Okay, full-fledged positive charge because it has one more proton. Then it has an electron, so it net positive one. Okay, well, the water molecule has a lot of partial negative around it because of the oxygen, and so it kind of surrounds the positive ion of sodium. The opposite, the other end of the picture is the, let me change the color a little bit, is the chloride. If this were, let's say, sodium chloride table salt, well, we would have on the other side the chloride ion, and those would be interacting there all around, okay, with the positive side, the partial positive of water. And so that's how the water will solvate a lot of its species that it has, that it dissolves. Okay. Very, very unique. All right, so let's just quickly summarize bonds versus forces. In the bonds, we have ionic bonds. Obviously, we have that holds the metal and non-metal ions together. Okay. That's the criteria. Ionic bond requires a metal and a non-metal. Polar covalent bonds are those non-metal bonds that share that bond unequally, making them polar. Okay. And I can't overemphasize that scenario where you have the A-B scenario. Okay. Where A and B are two different elements, automatically polar. We're talking about the bond, not the molecule right now. Okay. And then non-polar covalent bonds, again, two nonmetals, A and A, which are the same, and those electrons are being shared equally. The forces that we're dealing with, so we got three types of bonds: ionic, polar covalent bond and non-polar covalent bonds. Okay. And then we have the four forces that we're going to work with. The London force is the weakest, the dipole-dipole medium, and then hydrogen bridging force. It's only for nitrogen and hydrogen, oxygen and hydrogen, fluoride and hydrogen. Okay. And then we have the ion dipole force, which deals with aqueous systems, but we're dealing with ionic compounds. And so when we're dealing with covalent bonds, we are using the first three. And the last one, we're dealing with ionic bonds, ionic compounds in aqueous systems. All right. All right. So let's take a look at this. They're asking you to do this. One second. Indicate the strongest IMF, intermolecular force, in the samples of these molecules. Okay. Well, they give you the molecules, and then the first thing you got to do is determine whether it's polar or non-polar. Once you know that, then you can assign an IMF interaction. And so we talked at length about carbon dioxide. We know that carbon dioxide has two polar bonds, but because the nature of the beast, so to speak, and its geometry, it's linear, the polar bonds cancel each other out, resulting in a non-polar species. Okay, just to refresh your memory. And how we did this is we did the Lewis dot structure. We did the Lewis dot structure for carbon dioxide a few times. Okay, and we came out with this structure right here. Okay, then from there, then we analyzed the bonds in each one and concluded that yes, I got a polar bond going in that direction and a polar bond going in that direction. Going in opposite direction tells me that they cancel out. Hence, I have a polar bonded compound that is non-polar because the polar bonds in the compound cancel out. Once I know that, once it's non-polar, then without question, the only force they have to deal with is London dispersion forces. Okay, PF3. Well, how do I know if it's polar or non-polar? Lewis dot structure. Okay, and once you do that, you would come up with this formula. So you might go back and refresh your memory. You'll see that you come up with this Lewis dot structure right there. And you're going to end up with a lone pair of electrons in the central atom. Okay. And if you recall, when we were doing Lewis dot structures, when you come up with lone pair in the central atom, it's polar compound, regardless of what's built there, what's there. You know, if this was another bonded fluoride, then we would probably have, if this was bonded, the fluoride bonded to the phosphorus, it's not the right compound, but if it was, then it would be tetrahedral, and then all the molecules, all the bonds will cancel each other out, so you have a non-polar species, right? But we have lone pair in the central atom, which causes, they occupy a lot more space here. The orbit occupies a lot more space with this lone pair. And so they cause that bond angle, to refresh your memory, to decrease. And when that happens, this changes the direction of the dipole, so they don't cancel out. So we have a polar species. So anytime you have a lone pair, at least one lone pair, polar compound. You got two lone pairs like water, very polar compound. So that answers that question. It's polar. Now you have to figure out which force. Well, process of elimination. Go through what you know about it. Can't be number 4. Number 4 was the ion dipole interaction. Can't be that, right? Because there's no ions here. It's PF3, all covalent. So we can eliminate that. We found that it's polar, so we can eliminate the London forces. So we got two forces left over. We got the dipole-dipole interaction and the hydrogen bridging. Well, remember, in order to be hydrogen bridging, you must have hydrogen, hence the term hydrogen. Hydrogen bonded to either nitrogen, oxygen, or fluoride. We have fluoride here, PF3. However, there's no hydrogen. So we eliminate the hydrogen bridging. What's left? The only thing that's left is dipole-dipole. Okay. All right. Now we got HF. Very, very polar. Okay. Or I shouldn't say, just say polar. Okay. You say, well, how do I know that? Well, okay. HF, isn't that scenario with the HB scenario? Okay. Totally two different elements. Automatically, you got a polar species. Okay. And it's linear. So, you know, that bond's not going to cancel anywhere. So you got a polar species. All right. No questions asked there. We straightforward the polar. Now, being polar, you eliminate the London and eliminate the ion dipole, right? Because there's no mention here about ions. We're not talking about an aqueous system. So what you got left is dipole-dipole, which is possibility, or hydrogen bridging. Well, this falls in the category hydrogen bridging because it is an example of hydrogen bonded to fluoride. And that is one of the examples that you get hydrogen bridging when you have hydrogen bonded to nitrogen, oxygen, or fluoride. I keep overemphasizing that because it might be important. Okay. All right. We got carbon, hydrogen, and that's it. Carbon, hydrogen. Should bring up a flag. Hydrocarbon. Okay. Hydrocarbon, nonpolar. Nonpolar, London forces. That's it. Okay. All right. Now we have Ki. Ki, K is potassium, I is iodine. We got a metal, non-metal. We got an ionic compound, right? In an aqueous system. All right. So this is an ionic compound in a polar water. It's because water is very polar. Put that in long-term memory. Water is the most polar solvent out there. Okay. Since we got polar water and it's ionic, the only force that you deal with here is the ion dipole. Okay, so if I were to compare, let's say some of the parameters, I want you to do something here based on what we just talked about. We said that the strength of the interaction was hydrogen bridging is the strongest, followed by dipole-dipole, followed by London. Okay. And that's the strength that molecules hold on to each other. Now, with that in mind, knowing that when you heat these guys, you're breaking up that interaction. And so obviously the ones with the weakest interaction would boil away. It's easily to break away. Okay. To break the interaction between the molecules so they go into the vapor phase. So of these four here, okay, this one and this one with the London forces, carbon dioxide and methane would have the lowest boiling point at room temperature. And the fact that this is true is because both of them are gases at room temperature. They boiled a long time ago, temperature-wise. There's very little. London forces are extremely weak. And then the next, all we can do is give you a relative boiling point. Okay, we can't give you an exact number. We just say, well, relative to this boils greater, this boils less. So the next one batch to boil at a higher temperature would be the dipole-dipole, because that's the next one up. It has a little bit stronger force, so they hold on to the molecules a little bit tighter. And then the one that will have the highest boiling point will obviously be the London bridge. Okay, because that's the strength. And that's the type of compare and contrast that we can do. We can compare and contrast two compounds. We don't need to know their exact boiling points or the exact properties, but we can do a relative, this would be higher than this one, simply based on the polarity of the compound and then assigning to it a intermolecular force and then knowing which force is strongest as far as energy. And then we can make a deduction as to who we anticipate to have a higher boiling point, because we're going to be looking at some physical properties. Boiling point is just one of them. Okay, just one of them. We're going to be looking at, let me see if this slide. Oh, okay, before we talk about that, I need to talk about these interactions very briefly. Now we bring in this equation, and I don't want you to get all freaked out when you say we got a mathematical equation. That it's not that. Kind of demonstrate something here, what type of the effects you have between interaction and forces of interaction. And we can show that by using what's called Coulomb's law, which is an equation that gives us a measurement of force between two charges. Okay. And what has been found was that interaction between two charges, and we're talking about either a full-fledged negative, full-fledged positive, or a partial negative, partial positive, that type of intermolecular forces we're dealing with, that the force between them is directly proportional to the charge. Okay, that makes sense if you think about it. And what I mean directly proportional in mathematical terms is if I change one variable, the other variable the dependent variable would increase by an X amount. One goes up, the other goes up. You know, both variables change proportionally. Okay, it's a direct relationship. And there's a direct proportional relationship between the magnitude of the charge. And again, that makes sense if you think about it. If I got a positive charge, and then I double that to a +2 or +3, I'm going to have greater force, right? Makes sense. Greater charge, more force. We also find that it's inversely proportional to the distance square. Well, what that means again is this, that inversely proportional means that when we change one variable, the other variable drops. Okay. Proportional would be this: I study hard, I get good grades. Inversely proportional would be this: I study hard, I get bad grades. Okay, that's extreme example. You want proportional, right? Study hard, good grades. You don't want the other way around. So, but the square, the distance between them really makes a big change in magnitude of the strength. And you don't need a mathematical equation to tell you this. You probably already know this. You know, if you ever taken two magnets and let's say you put them together south by south or north by north, okay? Well, as you bring them together, you know, and they're pretty hefty magnets, you can feel the force of repulsion, right? You can really feel it as you bring them real close together. That force is really, really strong. You can feel it. The closer I get, that force gets stronger. And the same is true as the attraction. If I get, you know, something that's positive, negative over here, or north and south magnet far away, yeah, the force is there, but it's minute. But as I bring it together, you can see that force gets stronger and stronger and stronger. And the closer I get it, the stronger it gets. Okay. And that's basically what they're saying here. And we get this equation here. And I just want to graph and numerically demonstrate the magnitude of change that the square of the radius has between these charges. So we have the Coulomb's law that says the force is equal to some constant K, and then Q1 and Q2, which happens to deal with the charges. So what I'm going to do is I'm going to simplify this equation, and we're going to hold K is constant, and we're going to hold Q1 and Q2 constant. And if I'm holding all these constants constant, I can make one constant. Okay, so I can say, I rearrange this and I'll say, okay, force is equal to, and I'm just going to say X, okay, X encompasses the K and the Q's and make one variable. And then I got radius square. Okay. So now we're going to measure the force. So let's say, for example, I'm going to make radius 1 unit of distance. 1 unit could be whatever you want to call it, but I'm just call it 1 unit. I just want the numerical value. And so when R equals 1, guess what? The force equals X, whatever X would be, because 1 square is 1, right? And so the force is just straightforward X, whatever X may be. Okay. Well, let's do something a little bit different. Let's double the distance away. Okay. Double it away. In other words, we start off with 1 unit. Let's double the R. R becomes 2. Have we not doubled the distance, the radius? 2 units. And so now force is equal to X divided by 2 squared, right? Which 2 squared is 4, so it's X over 4, which is basically 1/4 X. And so by doubling the distance between the two charges, what you in effectively have done, you have decreased the force by a quarter, by 25%. That force has gotten less by 25% a quarter. And it makes sense again with the magnet. You got them real close together, they're repelling each other. I got two south ends repelling each other. The force is strong. As I double my distance away, that force decreases quite a bit. All right. So that is moving away. But what happens if you go the opposite direction? And now instead of, we went R, the radius is 1, let's cut that by half. Let's make R is equal to 0.5. That is half the distance we started off with. Okay. And so now we got X is equal to 0.5 squared, which is X is equal to 0.25, which means that X is equal to 4 times the force. Okay. And so by decreasing that distance by half, you have increased the magnitude of that force by a factor of 4. You have quadrupled that force between those two charges, just by simply reducing the distance between them. Okay, and these magnetic forces can be very strong. A lot of trains use these magnets to repel each other, so we have a vehicle literally gliding on air. Okay, so that's what we need to just take away, that the force is directly proportional to the charge, okay, and inversely proportional to the square of the distance. All right. So we have a list of questions here. And the thing to remember when you're answering these questions is to read them carefully, right? Don't skim over them, because sometimes the question will be misread, and then you're not sure what they're talking about, because we're basically doing two things, one or two things. One, the question is asking about the forces between the molecules or the forces within the molecule. And if you misread it, you're might select one over the other, which would be incorrect. So let's take the first one. What holds the atoms together in one ammonia molecule? Okay, one. So we have to figure out what type of bonds are being held in the nitrogen and the hydrogen. Polar bonds, right? And they're covalent. And so these are polar covalent bonds, because we're talking about one ammonia molecule. All right. Second question is this. Oh, bear with me 1 second. Hold on. Okay, I'm back. Second question, what is holding sodium ions in water? Okay, so let's break that down. We're dealing with sodium ions, ionic, and we're dealing with water, which is an aqueous system. So we got sodium dissolved in water. So, we're talking about intermolecular forces here, specifically the one that was listed as number 4, which was the ion dipole force. Okay. Number 3, what is holding 3 HCl molecules together? 3 of them. And so we need to first determine HCl. Is it polar, nonpolar? Obviously, it's polar. Okay. So we can eliminate London dispersion forces. We can eliminate ion dipole forces because there's no ions being talked about, ionic ions being talked about here. And so then the last 2 choices are either dipole-dipole or hydrogen bridging. It's got hydrogen. However, it's not bonded to nitrogen, oxygen, or fluoride. So the only thing left is the dipole-dipole. Okay, so dipole-dipole forces is what is holding 3 HCl molecules. What is holding the ions together in salt, sodium chloride? And so think about this. What is holding them together? We're not talking about an aqueous system. They're not dissolved. So we're talking about salt in solid form. And it's a metal and a non-metal. The only thing that it can be would be a ionic bond. Okay. Certainly not covalent. The sodium is a metal. Okay. What is holding 4 H2O molecules together? Okay. Well, we'll break it down. We know that H2O is extremely polar. Water is polar, no question about it. Automatic fact. Okay. Has nothing to do. So if it's polar, eliminates the London dispersion forces. We got nothing to do here with the question concerning ion, so we can eliminate ion dipole force. And so now we got either dipole-dipole or London dispersion, excuse me, or hydrogen bridging force. Okay. Well, we see that it's H2O. We see this hydrogen bonded to oxygen. The only thing it can be is hydrogen bridging. Yes, we understand there's a dipole-dipole. Okay. That's understood. But because it's a hydrogen bonded to oxygen, there's an additional force that's much stronger and overtakes the dipole-dipole interaction. It's called hydrogen bridging. Okay. Remember that. Yes, it's understood. There's a dipole-dipole interaction. But I overemphasize this. But because it's hydrogen bonded to oxygen, hydrogen bridging force is the number 1 force there for water. The next one, what holds nitrogen gas molecules to each other? Nitrogen gas, you got to remember that is a diatomic element. Nitrogen gas. They didn't say nitrogen atom, they said nitrogen gas. So it's N2. N2 diatomic, guess what? Nonpolar. Okay. That being the case, the only force that it has is London forces. All right. Then what is holding the oxygens together in an oxygen gas molecule? So we're talking about the bond in oxygen. Okay. And so we know it's covalent. So it's a covalent bond, but we have to be specific as to what type. Since it's O2, which is 2 of the same atoms, right? It's the AA character, which means it's nonpolar. So it's nonpolar covalent bond. Then what is holding 2 ammonia molecules together? Well, if you forget ammonia, remember, this is one chemical that hopefully we used it so much that you may just want to put this in long-term memory. Here's the formula for ammonia, NH3. And when we do the Lewis dot structure for that, you end up with this. Guess what? We got a lone pair in the central atom. Guess what? We got a polar compound, polar molecule, polar bonds and polar molecule. Okay. All right. So we have hydrogen bridges, right? Because again, it's polar and it's hydrogen bonded to nitrogen. And it's one of the three elements, NOF. All right. All right. This is what I want to do. I want to I'm going to stop at 13. Let's stop here on slide 18. Let's stop it here. We'll continue with this one next Friday, and then jump into some 15. And yeah, we're moving along pretty good.